I don't think we have a much choice here. We already have our microcontroller. We have been discussing 8051 microcontroller, so we will use this 8051 microcontroller as our microcontroller. And then for our ADC, we have recently discussed about ADC 0804. That will be our ADC. For the display, we'll be using a 16 cross 2 5 cross 7 matrix LCD. We are very familiar with this LCD, and we also have used LEDs. We'll be using two LEDs. We'll be using a green LED, and we'll also be using a red LED. We might have to use some resistors also for the interface of these LEDs, and then we have to use a thermistor for measuring the temperature, for monitoring the temperature. We can choose any thermistors. Thermistors usually have different temperature resistance profile. What I mean by temperature resistance profile is how actually the resistance of this thermistor, of a particular thermistor, changes with increasing or decreasing temperature. For example, in our case, since we are only concerned with a temperature range of 25 degrees Celsius to maybe something above 40, maybe up to 50 degrees Celsius. So let us assume that we have a particular thermistor whose temperature, whose resistance changes like this at 25 degrees Celsius. Temperature resistance at 25 degrees Celsius, it has a resistance of 1 kilo ohms. Maybe at 26 degrees Celsius, it has a resistance of 1.33 kilo ohms. And at 27 degrees Celsius, resistance increases further. Maybe it goes up to 1.80 kilo ohms. At some higher temperature, maybe at 40 degrees Celsius, resistance has increased further and it has reached to 13.5 kilo ohms. We are just assuming these things. When we'll be using an actual resistor, we can search for its specification sheet and we can get these curves, these relationships from there. So let's try to design a simple signal conditioning block. We have a 5-volt source, and to this 5-volt source we connect two resistances in series. We have a fixed 9 kilo ohm resistor, and then we have our thermistor. With changing temperature, the resistance of this thermistor will change, and accordingly the voltage at this point will also change. Let me call this voltage as VTH. So what will be the voltage? What will be the VTH? What will be VTH at 25 degrees Celsius? it will be VTH actually always will be equal to this formula: total voltage across these two resistors 5 into resistance of thermistor, which constantly changes with change in temperature, divided by total resistance 9 plus R 9 plus RTH. So at this is the general voltage. So at VTH voltage at this point, when the temperature is 25 degrees Celsius, since we know, we have assumed that the resistance will be 1 kilo ohms, so voltage at this point will be 5 into 1 equal to 1 plus 9 plus 1 equal to 10. That means 0.5 volts. And also we have assumed that at some point, maybe at 40 degrees Celsius, VTH at 40 degrees Celsius will be 5 into 13.5 into RTH, that is 13.5 kilo ohms, divided by 9 plus 13.5. Let me calculate that. 5 into 13.5, 5 into 13.5 equal to 67.5, divided by 9 plus 13.5, 9 plus 13.5 equal to 22.5. So 67.5 divided by 22.5 equal to 3. So the voltage will be 3 volts. So assuming, so we have two different values. We have temperature, and then we have VTH. At 25 degrees Celsius, this is in degrees Celsius, temperature is in degrees Celsius, the VTH is in volts. At 25 degrees Celsius, VTH will be 0.5 volts. At some higher temperature, 40 degrees Celsius, sorry, degrees Celsius, the voltage is 3 volts. So we can say, for a temperature has increased by 15 degrees Celsius, voltage has increased by 2.5 volts. So we can say with each 1 degree Celsius, assuming that the voltage increase is linear with temperature increase. That's not usually the case, but we will assume that for the simplification of our programs and simplification of our calculations. So we are assuming that the change is linear, that the dependency is linear. So that means for each degree Celsius increase in temperature, the voltage will increase by 2.5 divided by 15 volts. That means by 2.5 divided by 15, 2.5 divided by 15 equals to 0.167 volts or 167 millivolts. So basically I can write at 26 degrees Celsius, what will be the VTH? VTH will be 0.5 plus 0.167. At 27 degrees Celsius, VTH will be 0.5 plus twice 0.167. With each degree of temperature increase, voltage increased by 0.167 volts. At 28 degrees Celsius, we will be having VTH as 0.5 plus 3 times 0.167 volts. Okay. Is that clear? Now this VTH, what we are getting from our signal conditioning block, we are feeding this to our ADC, to ADC 0804, and we will be again assuming that we are not changing its reference voltage. So reference voltage is 5 volts, that's 0 to 5 volts. So this is an 8-bit ADC. Since this is an 8-bit ADC, output will be 8 bits long, and that means there will be 256 different states, and our step size will be equal to 8 divided by 256. That will come to, let me calculate this, 8 divided by 256, 8 divided by 256 equal, sorry, 5 divided by 256. This is 5, so 5 divided by 256, 5 divided by 256 divided by 256, that comes to 0.01953. Is that okay? So that we can also write as 19.53 millivolts. So that means when the input voltage V in, that's VTH, V in, that here equal to VTH, when it will be between 0 to 19.53 millivolts, the output of ADC will be something like this: 0 0 0 0 0 0 0 0 40 8 zeros, or we can simply say 0. And when the input is somewhere between 9.53 volts to twice 19, when the input is between 19.53 millivolts to twice 19.53 millivolts, output will be 0 0 0 0 0 0 0 1, that is 1. And when the input will be between twice 19.53 volts, I'm not doing exact calculations here because we don't need them, to 3 times 19.53 volts, output will be 2, that is 0 0 0 0 0 0 1 0. And this output we are actually feeding to our microcontroller. Is that okay? So actually the output voltage, the output number that we are giving to our microcontroller will actually be equal to V in divided by 19.53 divided by the step size. When V in equal to anything between, for example, 0, it will be 0. When V in equal to 19.53, it will be equal to 1. When V in equal to twice 19.53, D out will be equal to 2. Is that okay? And this V in is equal to VTH. This we have to remember. this is actually the relationship between input and output of the ADC. Okay, now we will actually discuss the relationship between the voltage between the output of our signal conditioning block, that is the input to the ADC, and actual temperature. This is the graph here, these are the numbers, this is the table here. Temperature changes, how VTH changes with temperature. So from this table we can deduce the equation between VTH and temperature. So we can write V equal to temperature, or I will call it, I have already called it as VTH. VTH is equal to temperature minus 25 degrees Celsius, because we are starting from 25 degrees Celsius into 0.16 plus 0.5, because voltage starts from 0.5 degree. It's actually a simple equation for a straight line between VTH and T. Y is equal to mx plus c. These are the initial intercepts. It starts from 25 and VTH starts from 0.5. So this is our second important equation for today. So we have two equations now. One equation relates our voltage, that is VTH, actually the output voltage from the signal conditioning, to the temperature, and then we have another equation, that's the relationship between output of ADC to the input of ADC, that is VTH. I will write both the equations again. So I have two equations. I have my VTH. VTH, you have to remember, is this voltage. This is my resistance of 9 kilo ohms, and this is my thermistor, and this voltage here is VTH. This voltage becomes V in for my ADC, and then I get an 8-bit data that I called D out, that actually I feed to the microcontroller. So VTH, this voltage VTH is equal to, we have already calculated it, will be equal to temperature T minus 25 multiplied by 0.167 plus 0.5, and D out equal to V in divided by 19.53, or we can also write as V in equal to D out multiplied by 19.53. This V in is also equal to VTH. V in and VTH are same. That means D out into 19.53 should be equal to T minus 25 0 point multiplied by 0.167 plus 0.5. Or from this equation, rearranging this equation, we can say that temperature actually is equal to D out multiplied by 19.53 minus 0.5 divided by 0.167 plus 25. I think I have made a small mistake in these calculations. It should not be here 19.53, it should be 0.0195, because everything else is in volts and only this is millivolts. If you remember, it actually came out to be 0.01953 step size. It was equal to 5 divided by 256. So this here is in millivolts, so I have to change this back to millivolts. So I have to write here it has to be 0.195 everywhere. So this will be 0.019, and also here I have to write 0.019, 0.019. This equation I will be finally using while writing my program. Now I think the equation is okay. I will again say this equation actually relates D out, the data out from the ADC, to the actual temperature. And how we have reached to this equation, I have already explained. We actually have a thermistor. That thermistor we have put in a circuit, and the circuit is something like this. We have 5 volts that we have given across a thermistor and a fixed 9 kilo ohm resistor. At the center of this we are getting a voltage VTH that is constantly changing, because the resistance of this resistor is constantly changing. And we have assumed that the temperature profile and VTH temperature resistance profile of this thermistor will be something like this. At 25 degrees Celsius it will be 1 kilo ohms, that it will gradually increase, and maybe at 40 degrees Celsius the resistance was 13.5 kilo ohms. So basically then we have also came to the conclusion that with the increasing temperature the voltage increases at VTH, and this relationship we have assumed to be linear. Since we have assumed that this relationship will be linear, we came up with a formula that VTH is equal to temperature minus 25 multiplied by 0.16 plus 0.5. And then since we know we have used ADC 0804 with 8-bit output, and thus its step size will be 19.53 millivolts, that will be equal to 0.0195 volts. We also know that D out will actually be VTH. D out will be VTH divided by 19.53. So we have a couple of equations. We have VTH equal to T minus 25 multiplied by 0.167 plus 0.5, and we also have D out equal to V in divided by 0.019. So We have rearranged these equations and finally come up with this equation, that is our temperature will be data out from the ADC which we are feeding to microcontroller multiplied by 0.0195 minus 0.5 divided by 0.167 and the whole we add 25. So this equation we will be finally using in our programming. So let's move on now to designing the hardware. First we will discuss about the number of pins we will be using. We are using our 8051 microcontroller. Again, we know that we have 4 ports and each port has 8 pins. That means we have port 0, we have port 1, we have port 2 and we have port 3. Each port has 8 pins. How many pins we need now? First, for the LCD we need 8 output pins for data, 8 pins for data. Let us select a port for this. Maybe we'll be using port 1. Good. And then we need 3 more pins for register select, for read write and for enable. We will be using, for example, pins P2.0, P2, or we can do one small modifications. Since in last program you might have seen that we always write to the LCD, we hardly read from the LCD, and in this case also we only have to write to the LCD. So we can, and when we have to write to the LCD, we have to keep RW equal to 0. So we can permanently ground this pin, RW pin of LCD. We can permanently ground, we can keep it permanently grounded. That will actually save one pin of LCD. So we will be using only 2 pins for control, RS and enable, because we only have to write to the LCD, and thus we can permanently ground RW. So RS and enable, we will be using P2.0 and P21. Then we have our ADC, and for ADC we have our ADC, and for ADC we also need 8 data pins. We need pins for read, we need a pin for write. I hope you will be remembering the ADC 0804. And we also need a pin for interrupt or end of conversion signal, INTR. Okay, so we can use one more thing. These LCD pins, all 8 data pins will be output pins. The 3, only now 2 control pins, they will be output pins. These 8 data pins of ADC will also be output pins. Read and write of ADC will also be output pins, but this INTR will be an input pin. Maybe we will be using port P2.2, P2.3 and P2.4 for controlling the ADC. And then we have 2 more pins. We have 2 LEDs. We have to use 2 LEDs. We might use port 2.5 and port pin 2.6 for these two LEDs. And then for ADC 8 data pins we will use a separate port, for example port 3. So I think everything is covered now. For LCD we will be using port 1 and 2 pins of port 2. For ADC we will be using port 3 and 5 and 3 more pins of port 2. And for LEDs we will be using 2 pins of port 2. That means we'll be using port 1 and port 3 completely, and we also be using 3 4 5 6 7 pins of port 2. Let me very patiently and very neatly, I will try to draw it very neatly, the hardware diagram, the circuit for this. This will be my microcontroller. Okay, fine. This is my LCD. Okay, that's also fine. Then I have my data pins. We have D0 to D7, 8 data pins, and these I am connecting to port 1. Is that okay? And then I have RS, register select, or let me draw RS from here. I have RS, register select, that I am connecting to P2.0, and I also have enable that I am connecting to P2.1. That's okay so far. And now I will be moving to other pins of my LCD.